Hi everyone. You have probably used HashMap countless number of times in your daily work or while solving lead code problems. But have you ever wondered how it actually works under the hood? If not, then this video is just for you. Let's dive in. So we know that HashMap is a data structure which stores the data in key value format. The first column in the HashMap represents the key and the second column in the HashMap represents the value. And the cool part about HashMap is if let's say I want to search any key, for example, John. So the search time complexity would be big O of 1 amortized, right? And if that key is not present in the hash map, then we'll just return null. So the goal of this video is to design such kind of hash map which can take any data type as a key and any data type as a value, and the search time complexity should be big of 1 amortized. If you are not aware about what amortized time complexity is, then I will explain that in the later part of the video. So let's start designing a simple hash map where the key and the value both supports integer data type only. So assume the problem statement is something like this. Given an integer array called nums, which contains all the positive integers and also one element, you need to find the index corresponding to this element if it is present. So for example, if the element is 9, you need to return 5 because that 9 is present at index 5. And if element is not present, for example, let's say instead of 9 we have 10, then 10 is not present in this array, right? So in that case, I have to return -1. So one data structure that is very optimal for this problem statement would be HashMap, because here the searching is O of 1. I just need to write map.get9. It will directly return me the index corresponding to that element, which is 5 in big of 1 time complexity. But for a moment, just assume that your programming language does not have inbuilt hash map, because ultimately we have to design this hash map, right? So let's say there is nothing called as hash map in your programming language. So now you have to come up with a data structure which will find the index corresponding to 9 in O of 1 time complexity. In other words, it should satisfy this particular formula. Can you think about any data structure where you can access any element in O of 1 time complexity? I can think about array, because in an array you can access any index in O of 1 time complexity. So let's try to come up with an array where this statement holds true. So now we are using an array data structure in order to represent the hash map. And the point that you should observe is if I do map.get9, it will return me 5. And this is the condition that we wanted, isn't it? And let's say if I do map.get10, it will return -1. So we have successfully designed a hash map wherein the index of any element is returned in O of 1 time complexity. But how this became possible? So I made one observation. The observation was something like this. So you can clearly observe one thing. The 5 in the input array goes to the output of this map, and the 9 in the output of the input array goes to the parameter of the map. So in simpler words, the positions of 5 and 9 are interchanged. The 5 was this particular 5, right? and this 9 over here is this particular 9. So we have interchanged the element and the index. So what I have done is this particular element that you are able to see over here now becomes the index in the map, and the index in the input array becomes element in the map. So if we interchange index and the element, we will successfully construct the hash map where the time complexity for searching any index corresponding to element would be big of one time complexity, right? But this approach has certain drawbacks. We'll see the drawbacks. So the first drawback is we are wasting a lot of space. So for example, in the input array, there were 6 elements. But in order to accommodate those 6 elements, we constructed the map of size 13 plus 1. Right? Why 13 plus 1? Because the maximum element in the input array was 13. And we know that element would be converted into integer. Right? And that's the reason why we constructed an array of size 13 plus 1, or maximum value plus 1. Now assume instead of 13 we had something like 1e5. So in that case we would have constructed an array of size 1e5 plus 1, isn't it? And most of the indexes in that array would just have -1. So we are wasting a lot of space by just having this -1s. And this is our first drawback. The second drawback is, what if the elements are negative or any other data type like string? So currently the element was positive, hence we were able to transform that into an index. But what if this element was negative? Can we transform that into index? No, right? Because we cannot have -2 as the index of any array, right? And second thing is, instead of integer array, what if we had array of strings? In that case, obviously we cannot convert a string like, let's say, shub to index, right? We cannot do so. Hence, these are the limitation of this particular approach. So we have to somehow eliminate these two drawbacks so that our hash map becomes scalable and flexible. So let's come up with optimal approach. So we'll try to eliminate both of those drawbacks. So the first drawback was we were wasting a lot of space. So the counterpoint for that would be we will not waste a lot of space, right? So what I've done is, instead of initializing a huge array, now we are just initializing a small array which is of size 4, right? So we have successfully eliminated the first drawback because the size of this hash map is just 4 and we are not wasting a lot of space. The second drawback was, earlier our hash map did not support different data types like string. So what we'll do is, in order to overcome that, we'll try to work with a test case where all the elements are string data type. Now, if we are able to come up with the approach where this string data type are supported, then I think we can also use any other data type in place of string. Okay. Now, earlier what we were doing, we were taking any element, for example, this element, and we were converting that element into index, right? But how can we convert a string to an index? So for that, you should know something called as hashing. So hashing is a process where you pass a key to the hash code function, which in turn converts that key to an integer value, and that integer value falls in this particular range. So let's try to convert this element into an integer value. In Java, we have this hash code function inbuilt for wrapper classes like string, integer, etc. So we just have to call this particular function. And one thing that I want to show you is, let's say, so the integer corresponding to this element is this particular thing, right? So shub, that is this element, will be converted to this integer. But can you see this integer over here? No, right? Our hash map is of size 4. So the integer that we wanted was in the range 0 to 3. So in order to obtain that integer, what we'll do is we'll mod this number by size of the map, right? So the size of the map is 4. So let's mod this up. So now we are getting the index corresponding to this element, and it is 2. So index corresponding to that element is 2, right? So what we'll do is we'll put this element into the index number 2. And one thing that I want to highlight is this particular box is called as index, right? So instead of indexing, going further, I will address this as bucket. So basically, bucket is nothing but index. Okay. So now let's try to find the index corresponding to this element. So index of this element is 1. So current will go into bucket number 1. Now let's try to find the bucket corresponding to ls. So ls will go into bucket number 0. Well and good. Now let's try to find the bucket corresponding to Bob. So Bob will go into the bucket number 1. But wait a minute. This particular bucket is already occupied by Karan. And one more element is going into the same bucket. And this particular scenario is called as collision. So collision is nothing but a scenario where two different keys wants to go into the same bucket. So we have to somehow put this Bob into this bucket, right? Because if we don't put this Bob into this bucket, then if a search query comes where we search Bob in this map, then we will find that Bob is not present and will return null. But Bob should be present, right? Because we have inserted this Bob. Hence, we have to somehow accommodate this Bob into this bucket. So how can we do that? So earlier our map was storing string data type. But now what I'm saying is, instead of storing string data type, we'll tell our map to store linked list at each bucket. So in the bucket number 0, we would have one linked list. In the bucket number 1, we would have another linked list, and so on and so forth. And this red box that you are able to see is nothing but the head of the linked list. Okay. So currently I have inserted the first 3 nodes into this map. Now let's try to insert this Bob. So we already saw that Bob also wanted to go into bucket number 1, that is this particular bucket. But now, since this bucket has the linked list, what we can do is we'll just extend the linked list like this. So this node will have Bob. Now let's say one more query comes where I need to insert Tom, and assume that Tom also wants to go into the same bucket, that is bucket number 1. So again we'll do the same thing. We'll extend the linked list. Right. So this is how we are able to overcome the scenario of collision. But can you see one drawback over here? The drawback is, let's say we keep on inserting different keys. Like let's say one more insertion comes, and let's assume this particular key also wants to go into the same bucket. So we'll extend the linked list. Now let's assume a search query comes. Search A. And by the way, this would be A, right? So in order to search this element, first we will convert this element into the corresponding index. So index of this would be 1. And then we would have to iterate this linked list. And once we reach at this particular position, we'll return true, indicating that yes, this particular key is present in the hash map. But the time complexity of this would be O of n. But we were supposed to build a hash map where the time complexity of searching should be O of 1, isn't it? Hence, if the size of the linked list keeps on growing, the search complexity will also grow. So we have to somehow restrict the size of this linked list. Let's say I want my linked list to not go beyond this limit. If I'm successful in getting this done, then I think we can reduce the searching time complexity. But how to achieve that? So here comes the concept of load factor. So load factor is something which restricts the size of the linked list. And by the way, you have to remember this formula. So the most commonly used value for the load factor is 0.75. So the formula says that if the total number of nodes in the hash map becomes greater than the load factor into map.size, then you have to call the rehash function. Right? So over here 0.75 into 4, the size of the map is 4, that's why 4 is equals to 3. So if the total number of nodes in the map goes beyond 3, then you have to call rehash function. Now, what does this rehash function do? And why are we calling this rehash function? We'll try to answer both of this question. So first we'll start, what does it do? So it basically constructs a new hash map of double the size of the current map. So currently the map size was 4, and now we constructed the map size of 8. And second thing is we have to now transfer all these nodes into the new map. So let's do that. So currently ls is present at bucket 0. Now let's check where it will go into the new map. So for the new map, the modulus would be mod by 8. Again, ls will go into the bucket number 0. Karan will go into bucket number 1. Tom will go into bucket number 2. And this is how I have already filled this new hash map. So the point that I wanted to highlight is now if we try to perform the search operation on Tom in the old map, that is in the current map, then it would be big of n time complexity. But the same search function on Tom would be big of 1 time complexity over here. Because, and this is the advantage of calling rehash function. I hope the question of why are we calling the rehash function is cleared. So now let me show you why 0.75 is the most commonly used load factor value. By the way, load factor value can range from 0.1 to 1. So let's assume we go on the extreme right side. So in that case, this formula would become something like this. So assume we have one hash map of size 4. So this formula says that if the total size or if the total nodes in the map goes beyond 4, then call rehash function. But if it is 4, then we will not call rehash function, right? So I have constructed this map with a linked list of size 4, and we will not call rehash function because for calling rehash function, we should have greater than 4 nodes. So now let's say a search query comes on Jake. So obviously we have to first go to this bucket and then iterate this linked list. And that's the reason why the time complexity would be big O of n. So one conclusion that we can make is if we go on the extreme right side of this line, then the time complexity would be big O of n because of search function. Now let's try to go on the extreme left side of this line. So I have taken 0.1 as the load factor value. So in that case, we'll get 0.4, which is again, we can say it is 0. So if the total number of nodes in the map is greater than 0, then we have to call rehash function, right? And it means that after every single insertion, we are supposed to call rehash function, isn't it? And the time complexity for rehash function would be big of n because we are transferring the nodes from the old map to the new map. Hence, the conclusion would be if we go on the left side, the time complexity would be big of n due to rehash function. And if we go on the right side, again the time complexity would be big of n due to search function. So for optimal time complexity, we have to stay in between. And Java uses 0.75 because of this reason. So 0.75 would be somewhere over here. Okay. So I hope you understood why we took 0.75. So now let's analyze the time complexity for put, remove, and get functions. The worst case time complexity would still remain big O of n. Let me explain this. So let's say we have a hash map of size 8 and we will call rehash function on this hash map when this condition will become true, right? So what I'll do is I'll not make this condition true. So the total number of nodes would remain on the borderline, which is 6. So I have introduced 6 nodes A, B, C, D, E, F. Now, if someone comes and tries to search F, so the time complexity for this search would be big O of n, right? And that's the reason why in worst case, the time complexity would still remain big O of n. And that is true for the inbuilt hash map as well. So now let's try to analyze the amortized time complexity for put function. So let's say we have an array of size 4. Okay, so this is basically is our map. So first query says that we have to insert key is equals to a, right? So let's assume that this key will go into bucket number 1. Okay, so I have inserted this particular key into bucket number 1. Now let's say second query comes, which is insert b. So let's assume that key is equals to b will now go into, let's assume, bucket number 0. Okay, now let's check out for this query. So assume this particular key would go into bucket number 2. So till now all the insert operation took big of 1 time complexity, right? Now insert d comes. Okay, I have to insert d. But before that, I wanted to reiterate the formula, that is, total nodes should not go beyond 0.75 into 4, which is 3, right? If it goes beyond this value, then we have to call rehash function. And since we are supposed to insert the fourth node, we have to call rehash function. Hence, a new map of size 8 would be constructed and all these nodes would be transferred into that map. And that's the reason why the time complexity would be big of n. So total time complexity of all this operation is 2n. N for this operation and almost n for the other 3 operation. Okay. And total number of operations are n operation, right? N means 4. 4 operations are performed. So amortized time complexity is calculated by this formula. Total cost upon total number of operations. Cost is 2n and operations are n. So the resultant is a constant value. And this is the reason why I have written of 1 over here, which is constant. Now let's try to analyze the amortized time complexity for get function. So assume the hash map is of size 8 and these are some of the nodes which are already inserted into that hash map. The first query says that we have to search element A. So what we'll do is we'll try to find the bucket for element A, and once we reach this bucket, we'll directly see that A is present over here. So we'll return through. So the total operation taken is 1. Right. Now for searching B, we have to first go into this bucket and traverse this linked list by 1. And that's the reason why total operations taken is 2. For C, it would be 3. And for D, it would be 4. And again for E, it would be 1 operation. So total number of operation taken are 11. And we know that amortized time complexity is calculated by cost upon operation. So cost is 11 and operations performed are 5. So 11 upon 5 is 2, which is almost constant. Hence, we can say that the amortized time complexity for get function is O of 1. Similarly, amortized time complexity for remove function is also O of 1. So I hope you understood why in worst case we have O of n time complexity for all these functions and why we have O of 1 amortized time complexity for all these functions. So now let's check out the code. So I have implemented the custom hash map where the data type for the key is string and for the value is integer. Okay, and this hash map is flexible enough to support any other data type as well for key and value. So I have first inserted all these entries into the hash map and finally we are trying to find the marks corresponding to these students. So let's check out whether this get function is working or not. So marks corresponding to John is 78. Yes, it is true. And for Bob, since Bob is not present in the hash map, we are returning null. So we can say that hash map is working perfectly. So let's check out the implementation of this custom hash map. So basically I have defined some of the variables. The first one is initial size, which represents the size of the map initially. So as you remember, we started with a map of size 4. So that's the reason why the initial size would be 4. The max capacity is 2 to the power 30. So I am using this variable because the array that we are using to construct hash map also has some limit, right? We cannot scale that array indefinitely. So above this limit, what I'll say is that we cannot perform rehash function, because rehash function is the one which doubles the size of the array, right? Then the third variable is load factor. We know that this is the commonly used value. And the fourth variable is total number of nodes currently present in the custom hash map. So we'll start with the map. We'll start with the array of linked list. Okay, so this is array of linked list. So let's check out the node class. So this is how the node class would look like. So linked list consists of many nodes, right? So this is one such node. This is how one such node would look like. So earlier we were having, or we were working with this node, right? Wherein only one element was present. But now we are working with key value pair, because HashMap has a key and a value. And the hashcode function would be called on this key parameter. Okay. Because we have to perform search function on this key. That's why we have to use hashcode on this key. Right. So I have defined a key and a value. And by the way, I am using doubly linked list. And that's the reason why I have a next pointer and a previous pointer. And I have used generics over here because I want my hash map to be flexible enough. That is, the key can be of any data type and value can also be of any data type. So I hope you understood this node class. So now let's check the constructor. So for the constructor, what I am doing is I am first creating an array of size 4, and in each bucket I am creating two nodes. The first node is head and the second node is tail. So the head's next is pointing to the tail and tail's previous is pointing to the head. Let me show you this in the diagram. So this is what we are doing. So at each bucket, we are creating two nodes, head and the tail, and the pointers are pointing to one another. Okay. So this was the constructor. Now, these are the main function for the hash map, and these are the helper functions. So let's see the find node function. So what this function does is, so it will take the key as the input and return the node where that key is present. Okay. So for that, what we'll do is we'll find the bucket number where this key should be present. Okay. So we'll get that bucket. We would have the access to the head of the linked list, right? So once we have the access to the linked list, we have to just iterate through the linked list. And if we find any node where the key of that node corresponds to the key given in the input, then we'll return that node. Else at the very end, we'll return null. So this is how we find a node where this key is present. Okay. And this find node function is used in all these main functions. So let's see the put function first. So for put function, we have to insert this key value pair into the hash map. Okay. And we also know that in the hash map, key should be unique. So we'll first try to find the node where this key is present. And if that node is there, in that case, we just update the value of that node and return from here only. Else, we find the bucket for that key and we get the head of the linked list. Then we perform certain operations. So let me show you these operations. So this is how our hash map would look like initially. So after this, what we'll do is, let's say the first query says that we have to insert shoop comma 90. So in that case, we find the bucket. So let's assume the bucket was 2, bucket number 2. So we will insert this node just below the head. Okay, we are inserting this shoop comma 90 just below the head. Now let's assume one more query comes which says insert Leo comma 70. So we are inserting this node just below the head. I hope you are understanding this thing. So if any node comes, we would insert that just below the head. So in order to insert any node just below the head, we have to know two things. The first is head and the second is a node which is below the head. So this is the old first. So for example, old first would represent shoop comma 90 when I will be inserting Leo, and head would represent the head. Okay, and this is the new node that we would be inserting. So heads next will point to the new node. Heads next will point to the new node, and new nodes next would point to the old first. New nodes next would point to the old first, and new nodes previous would point to the head, and old first previous would point to the new node. Okay, so I hope you understood this operations. So after inserting this node, I will increment the counter, and you know that once this condition becomes true, we have to call rehash function, where the new size of the map would be 2 into the current size. So let's check out the rehash function. So again, what I'm doing is I'll first verify whether the new size is within the max capacity. If it is not, we would return from here only and we would log this message. Then we would construct an array of new size. Okay, and again we are going through each and every bucket and creating head and the tail, and both of them will point to each other, right? Then we would iterate through the old map, like we would go through each and every bucket, and for each and every bucket we would go through entire linked list, right? And we are basically ignoring the head and the tail. Okay, so basically when we are traversing, let me show you over here. Okay, so this is how rehash would work. So we would go through each and every bucket, and for each bucket we would go through entire linked list, and we would basically ignore this head and the tail part. Okay, we would just consider the middle portion. In this case I have not drawn, but just assume that there is one head and the tail. So we are ignoring that head and the tail. Then after that, we are trying to find the new bucket number. Okay, how can we find the new bucket number? Same thing, but now we would divide by new size and get the remainder. Okay, so this is how we get the new bucket number, and we get the access to the new head of the linked list, right? and this is the old first in the new bucket. So let me show you. So let's say the new map looks something like this. So this is the head, this is the tail, and this is the node that is already present in this linked list. Now this would be the head of the new linked list. So let's call this as new head, and this would be old first. Okay, right? And this would be new next. Currents next would be new next. So this is current. Let's say currently, so let's say we are iterating through this linked list, and currently our current pointer is pointing to this node. So let's assume this is current, and this would be next node, right? So what I'm saying is new heads next would point to current. Okay. So new head, that is this, the next of this should point to current. So let me bring that over here. So next should point to current. Okay. And current's previous should point to new head. Current's previous should point to new head. Current's next should point to old first. Current's next should point to old first. And old first previous should point to current. So this pointer will point to this thing. Okay. So this is how we are rehashing. This is how we are moving a particular node from this linked list or this map to new map. Okay. And finally, this current will move over here. So I have written that over here. Okay. Then going further, we would use this map. So this would become map. Okay. Because now we will start using this particular map. Right. So I hope you understood the rehash function as well. Now, the get size function is very easy. We would just return the count of nodes. Okay. So we have seen the put function and get size function and rehash function. The remove function is also very easy. We first try to find the node where this key is present, and if that node is absent, it means that we are not supposed to remove any node. But if that key is present, then we are just manipulating the pointer. For example, let's say we are supposed to remove this node. So in that case, the next of the head, I mean, this is the previous node, this is next node. So the previous nodes next would point to this particular node, and this node would now point to this, and we would finally remove this. Okay. So this is how we perform remove operation and finally reduce the counter. Right. So let's check out the get function as well. Again, we will first find the node corresponding to this key, and if that node is absent, we would return null, else we would return the value corresponding to that key. Right. So this was the get function. So I think we have seen all the functions. So I hope you understood this implementation of HashMap. And one more thing that I wanted to highlight is, since we have implemented the HashMap, we have indirectly implemented the hash set also. So in HashMap, each and every node has a key comma value pair, right? So hash set will have a little variation of this. It will just have keys. That is, it will not have this value. So we can just comment this value, and the same code will become hash set. Okay. I hope you understood this thing. So if you found this tutorial useful, then please like the video and share this with your friends. Thanks.